Hi, all. Welcome. Today's speaker is going to be Drew Rich, and I wish you and Drew a very warm welcome. Thank you, Drew, for doing this. Drew is a PhD candidate in civil and architectural engineering at the University of Miami. Going directly from his bachelor's to his PhD, Drew began his research in eutrophication of Florida waterways, and then he transitioned into simultaneous demand estimation for design of international residential pumping systems. And he recently has submitted a patent on this with Drew as one of the two main inventors. In parallel with this research, he advises a slew of ICC standard development committees on standards dictating wastewater drainage systems, water reuse, water distribution systems, and sensor installation procedures and specifications. He has taken on a number of leadership roles here at UM, including positions as a graduate student senator, and he's also the department representative for the PhD advisory committee. Today, Drew is going to talk about development of an international design framework to optimize size premise compass systems. So thank you very much, Drew, for doing this, and it's all yours.
Cool. Thank you, Prannoy. And again, thanks again for the introduction. Like Prannoy had said, I'm going to be talking today about the development of international design framework to optimize and size premise plumbing systems. Now, before we get too far into it, I kind of want to talk about the presentation outline, right? I'm a big fan, and we always talk about it in the lab, a big fan of crawl, walk, jog, run, and then, for those of you who can fly, fly. But really just introducing you to the basics first before we get into the more complex analysis, right? So as I know, we're going to start off with an introduction, brief introduction about myself. Prannoy did a really great, thank you so much, Prannoy, for the introduction. But just to emphasize, I work a lot with the ICC, the International Code Council. So those are the folks that develop regulations and guidelines for development of buildings, right? So specifically, I work with the IPC, and right now we're working with the ICC 815 initiative that is working on designing a methodology that can size premise plumbing systems. I've also contributed to some other stuff, such as water reuse standards, where we just had a publication that was cited directly by them, and they took our work and kind of adapted it, and it is now going in through the code provisions to go into actual regulations. So super excited about that. But today's focus is going to be on the ICC 815 initiative, which again is on premise plumbing systems. Now, we've said that a couple of times. So let's talk about the background and really understand what a premise plumbing system is, right? So when we talk about a premise plumbing system, this is the portion of the water supply and wastewater collection system that is maintained by the owner or the property. So it's on site on the within the parcel, right? So typically a good way to think about this is when we talk about premise plumbing systems, we're considering this to be everything past the meter, right? So if there's not a present meter, it's really anything that's on site. Okay. Now, when we think of plumbing systems, they don't just exist in residential homes, right? There's a variety of different types of occupancies that require plumbing systems. We have industrial, assemblies like stadiums, institutional facilities, commercial buildings, medical facilities. So we have to understand that there's a very large, subset of buildings that need plumbing systems. But we wanted to narrow the focus down to specifically residential buildings, right? And the reason for that is because there are variations in how we use water based on these different occupancies, right? So if you think about an assembly area, so we're talking like a stadium, at halftime, you have a very massive influx of people that are using restrooms and the water facilities, whereas the single family home, those usage patterns are going to be different. So we really wanted to narrow the focus down to specifically look at these multifamily and single family residential buildings and how we can predict water consumption for them. Now, in order to understand how these systems are designed and how we actually traditionally size these systems, right, or select the demand estimation, we have to understand how they're laid out, right? So components of a residential plumbing system are designed in a tree-like manner, right? So they consist of multiple different pieces of equipment and components, but the primary ones we're going to focus on are going to be the pipes, right? So those are the actual mechanism for the deliverance of water. We have joints, which allow for water change direction. And then we have the terminal nodes or the fixtures. And these are the actual things that use water, right? Now, it's really important to note that we are constrained to 45 and 90-degree angles when we're developing these networks because of traditional manufacturing, right? So Traditionally, joints are restricted to make sure it's simplified to 90 degrees and 45, which is why we can't really vary outside of that those network constraints. Okay, so the lines have to be at 45 or 90 degrees. Now, understanding this, each pipe upstream or opposite the direction of flow, right? So if we're looking at a terminal node here, every pipe that's leading up to that has to be able to supply enough water and pressure for all of the fixtures downstream of it, right? So again, we have to look at designing with that in mind. But the question that I always ask people here is, when was the last time all of your fixtures were active at the same time, right? You had your showers going, your kitchen sink, your dishwasher, laundry, every single thing that activates or uses water you had running at the same time. Now, for most of you, I hope, the answer is never or very, very rarely. And if not, come talk to me. We need to discuss your water use habits and probably talk about water conservation. But either way, so with that in mind, it doesn't happen often, right? So instead of designing for this maximum possible flow rate, which has all the fixtures active at once, we start to talk about simultaneous flow or maximum simultaneous flow. And this is the highest total flow rate expected when multiple plumbing fixtures are operational at the same time, usually during peak conditions, right? So, okay, we understand that concept. We now know what simultaneous demand is, but why does it even matter, right? What's the big deal? Well, if we select a Q design or a simultaneous flow rate that's too big, we're going to end up with a pipe diameter that is also too large, right? And everybody might say, oh, that's not a big deal. We'll decrease the pressure losses, but we have other problems that are associated with that, right? So we have increased capital costs. If you're selecting a diameter that's too big, that material costs money, right? And it also takes up space. So you're not only increasing the capital cost, you now have a scenario where your water stays in your system longer, right? Because you have a higher storage capacity within the system. So that can actually lead to health risks associated with opportunistic pathogens, things like viruses, bacteria, protozoa that develop in your system and then can be transmitted through aerosolization to you, which can make you very sick and actually end up killing people. An example of that is Legionella. We have inefficient energy use, right? We end up tending to oversize the pipe to compensate what we expect to be a higher flow rate. And again, the high residency time can lead to a lot of water quality impairment. Now, on the other side of things, right, if we choose a Q design that's too small, we end up with a diameter that's too small. And that also is an issue because now we have higher turbulence inside the pipe. So that leads to increased pressure losses, and that can result in user dissatisfaction. So the thing that I always like to ask here is, you ever had a shower where you were going to take a shower, all of a sudden the pressure dropped out and you were, the water wasn't spraying hard enough and you couldn't get the soap off. So that's what low pressure looks like. So if that happens, we end up with user dissatisfaction, which is a major problem, right? Because again, these systems are designed to ensure water is delivered to the user, okay? On top of that, we have turbulent flows that can cause premature failure in joints and other components within the system, right? So we can have pitting, you can have failure associated with leaks, so not really a desirable outcome. And on the final end of things, we have an increased noise from turbulence, right? And again, it might not be something that a lot of us think about when we consider a failure, but at the end of the day, you really don't want to hear every time your neighbor is taking a shower, right? That's just not something that's desirable, right? So we want to try and focus on picking the correctly sized pipe, which requires a correctly Q design, correct selection of Q design, okay? Now, this is where the research knowledge and gaps come in, right? So traditionally, what we do to estimate demand, it's based off a methodology called the Hunter's Curve, okay? So the Hunter's Curve was created in the 1940s, okay, early 1940s. Since then, we've had a lot of changes in fixture users, fixtures themselves, my apologies, misspoke, fixtures themselves, specifically from changes in legislation to adopt more water conserving, really to optimize or incentivize, there's what I'm looking for, incentivize water conservation, right? So you can look up here at A, we have a major change in the amount of water that these fixture uses, right? So we look at a shower head. In the 1980s, which is around the time we started to change these things, we had shower heads that were at 3.5 gallons per minute. Since then, we've reduced the amount of water coming out of our shower heads by about 43%. Commercial laboratories, right? 86% reduction. Residential clothes washers, 67% reduction in water consumption. And, the big one, toilets, we've actually reduced by 74%. So this has caused a major shift in what we expect water patterns to look like in the built environment, right? So this arrow that we're showing here is the actual maximum demand distribution in today's systems has dropped significantly, right? So this little arrow here, this gap that we're seeing is actually what I consider to be the research gap, right? So we need an accurate methodology for determining simultaneous demand that's efficient and based on modern methods and data, right? The traditional methodology used probabilistic reasoning to predict. And again, we have a lot more technology that we can use to come up with a solution for this problem, okay? So in order to go through and make sure that this was the actual correct way to do things, we went through existing literature and we started to identify existing standards as well as existing research that has tried to tackle this problem, right? So that's identifying the research gaps within the research. So we knew that this was a problem, but what has other research done and how are those methodologies lacking? What we found was there was a lack of comprehensive data sets for validation. That was one of the first findings. Second one was there was a non-uniform data collection procedure, right? So for the people that did collect data, they were all doing it differently. Third, when we looked at the actual design and the methodologies to predict this demand, there was a lot of really regionally specific design criteria. And recent studies have actually shown that we can't just take the data from one country and apply it to another one. It seems kind of logical when you put it like that, but it's traditionally what's been done around the world, right? So the other aspect of this is that existing methodologies were inefficient. So it was making it very challenging to adopt these things, right? And finally, there's a very narrow scope on calculating flow rate, and it really lacked that holistic approach. So we were trying to create something that kind of responded to these gaps in the research, right? I'm going to take a quick drink of water. Through this, we kind of worked with the ICC A15 initiative, and we wanted to create a next generation approach to pipe size. So we kind of identified 5 key points that we wanted this methodology to exemplify, right? So first of all, we wanted this to be a global product, okay? So we didn't want this to be, something that we developed in the US and then said, okay, we did it here, let's go apply it to Australia, it's gonna work perfectly. Again, research has showed that that's not the case, okay? We wanted this to be a living document. One of the Hunter's curve was great when it came out, but the problem with it is it became antiquated, right? So the more time that had passed and things changed, it didn't really apply to current situations. So we wanted to make sure that this was easily updatable, right? The third thing we wanted was a simplified design approach, okay? So what does that mean? We didn't want this to be incredibly complex because at the end of the day, we need users or designers to use this to create our systems. If it's incredibly complex, nobody's really going to be able to actually use this. Okay? Then we want on the public health and safety side, right? So if we correctly identify the demand flow rate, we're going to then be able to optimize public safety. And again, we wanted this to be modular and adjustable. This needs to be able to adapt to various plumbing systems with various different designs and various different consumption patterns across the world. And all of this coming together is what we hoped ICC A15, the holistic pipe sizing standard, would create. Okay, so after all of this research, after this, we started to put together a plan, and this was our long-term research goals, right? So what do we want to achieve? At the end, like when this is all complete, what do we want to achieve? So the first thing was demand estimation. We wanted a tool to design or predict international residential water demand and sanitary load rates on given components in the plumbing system. This also extends to equipment, right? We wanted this to be easily streamlined and generated with computer automated design that could link into existing software and simplify the process, right? So we don't want to necessarily reinvent the wheel, but we do want to make something that's actually going to be used by designers and practitioners. We wanted to incorporate machine learning, artificial intelligence, and we also wanted to use our scientific tools to select appropriate demand curves. We wanted this to be internationally applicable. We've kind of already talked about that. And we wanted to create a data collection procedure that can optimize the or feed into our methodology to make sure that it constantly stays updated, okay? So with that in mind, I couldn't cover all of that in just one thesis. So the key things that we wanted to focus on for this thesis were influential factors, right? So how do demographic and regional factors influence water consumption events or the descriptive distributions? And then how did the second thing was going to be network-based sizing, right? So can we make this simulation into something that can automatically size these systems? And we're going to go into that a little bit later. The third thing was the uniform data collection, right? So none of this really works unless we have a uniform methodology that we can actually compare data from one country or region to another. And can we uniformize that data collection or standardize it to ensure that we're all looking at the same data and really make sure that this is a modular solution, okay? So with that in mind, you saw a lot about the previous methodologies that exist. So I kind of wanted to highlight some of the novel aspects about what my methodology brings to the table. First of all, there's been a lot of simulations that have been used, especially stochastic simulations, to predict water consumption. Now, what's novel about my methodology, or Esber and I's, is that we actually can apply these simulations to a network-based or a user-defined network. This allows us to size all of the pipes simultaneously, right? So it really improves on the efficiency of this. Second of all, we wanted to develop a methodology that allows for this regional adaptation. This is something that hasn't been really considered, especially when we look into influential factors and the different regional consumption patterns, right? So one of the things that I really want to highlight is the idea of IWSS, or intermittent water supply systems. These are actually systems that you don't necessarily have access to water all times of the day, right? So when we take the methodologies we develop in the US, which we do have access to water at 24/7, and we apply them to those areas, you could end up with a situation where you have a significantly undersized pipe, because when people get water in those regions, they all use it at once, right? You want to collect as much as you can because you might not have it for another 3 to 4 days. So the development of this methodology allows for this, again, we've said it a couple of times, but this adoption of the local constraints, right? The next thing is this incorporates the design of plumbing equipment as well as demand estimation, right? So because the simulation has all of these events, we can start to look at the inflows and outflows, and we can size equipment differently than the way we size pipes, which is not how it's traditionally done. And the final is the creation of a novel methodology that standardizes data collection, right? And we've talked about the importance of that. So this is the point in the presentation that we're going to start to explore factors that influence water consumption, right? So we did this through 2 different methodologies. The first was looking at, or we were trying to understand the consumption patterns. So in order to do this, realistically, we would need a high-resolution data set and metadata that match to that data set so that we can see how our high-resolution data sets changed with respect to the metadata. Now, there's a pretty big problem, and we're going to kind of touch on this multiple times throughout the presentation, but these data sets required to perform these analysis are very challenging to find and also very expensive. I think the last time we talked with one of our industry partners, we're talking on the scale of hundreds of thousands, if not millions, for these data sets, right? And that's unreasonable for anybody that's not a municipality that wants to look into this, okay? So we had to ask the question, what data sets are cheap and readily available that we can provide insight, not necessarily get a full picture, but provide insight on what factors influence water consumption? And this is something that I kind of thought about a lot, and we finally came up with the idea of using billing data. Now, you might say billing data, okay, that's every 1 month. How are you going to understand how water consumption events change based on billing data? Well, if you think about it, for a given event or a water consumption event, right? So if you turn on the shower for a given event E, the volume of that is essentially represented by a pulse, right? So we have a flow rate, or the height of our square or rectangle, and then we have the duration, which is the length. So that volume is represented by the area of this event. Now, if we take a series of events that happen throughout a day, or even multiple days in a billing cycle, if we sum all of those volumes, we end up with essentially our billing data that's billed. So we can really start to draw implications into what factors might be influential if we start to look at the billing data. Now, This isn't a perfect methodology, but it gives us a starting point, right? So what we did was we contacted WASDA, or the Water and Sewer Department in Miami-Dade, and they were able to provide us with a data set with approximately 500,000 metered properties. Now, this was eventually reduced down to about 430,000 because a lot of those are going to be commercial, industrial, stadiums. So we didn't want to look at all of those. We really wanted to narrow the focus. Each data point, or each point you see here on this map, contained about 16 years of billing data. And we were also able to obtain data from the American Census and American Community Survey, as well as Miami-Dade Property Point data, which described a lot of different characteristics of the actual home, okay? So those are very important, right? So for this study, we specifically focused on single-family residential because we wanted to kind of eliminate any bias that are going to be associated with cities, right? Because if you have 1 meter for a high-rise residential building, that could skew the data one way or another. So we specifically looked at single-family homes and the impact of influential factors. Now, there's 2 analyses that we performed in order to understand, or regressions essentially, the influential factors associated with this data. The first one is going to be the ordinary least squares regression, right? So this is, essentially a linear model that can combine all of these factors and predict outcome, which we decided to be daily water consumption, or average water consumption over a billing period. And then there was the second aspect, which is multi-scale geographically weighted regression. So essentially what this does is this looks at the individual areas that we were monitoring, and it creates an individual OLS for each one of them based on its geographic location and its neighbors, right? So we're using that point and its neighbors to try and predict or generate an OLS. And there was 2 kind of objectives here. First one was, again, those influential factors, but also, can we start to predict what water consumption is going to be based on these 2 different methodologies? Now, we're going to start to get into the results. I could talk a little bit about the actual data breakdown and the filtering, but it just seems like a lot for right now. For anybody that's interested in that, please feel free to reach out. We're about to publish that paper, or we're about to submit to publish that paper pretty soon. So I first want to share the OLS results. And, we can go more in depth, but first of all, we found some very significant impacted factors, right? As you can see on the right side here, we have maps showing the measured data versus the prediction of the OLS. Overall, not the best in the world in terms of the R-squared or the adjusted R-squared, reaching only about 0.67, but we did start to identify some of those factors that were very, very significant, right? A lot of them that were much less than 0.001 in terms of a p-value, and that's based on t-statistics. Okay, so in general, I kind of want to go over the overall trends, right? So from this data, we started to see that as money within an individual household, or as the money in an area, it starts to decrease, and we were able to look at that through access to internet, right? Food aid, wealth and income within a given household, right? So as that decreases, we noticed water consumption started to decrease as well, okay? In this particular model, we also saw that as population density increased, we saw an increase in water consumption, which is very interesting, right? And the other aspect is, as the characteristics of the home became a little bit more fancy, right? You had an increase in floors, the habitable building area increased, the assessed value increased. You also started to see an increase in water consumption, right? So that also kind of ties back into the financial aspect of this. And the other one that's really important to note right here, which I'll kind of touch on later, is that as the actual number of people in the household goes up, we start to see an increase in water consumption. And that's very logical, but we're going to see that come in when we look at the high resolution data as well. So the second analysis we did was the multi-scale geographically weighted regression. And there's a little bit of a different result here. So we don't use t-statistics, we use individual Pearson's R. Now you'll start to notice that the overall R-squared for the model itself is much, much higher. We're in the range of 0.89 to 0.88 for our R-squared, and around 0.864 for our adjusted R-squared. Now, you'll also notice that the R-squared value for some of these variables is significantly lower than we'd expect and doesn't really make sense. But what I want to point out is that this is looking at only the R-squared between that and the variable, right? So the variable that we're looking at and the overall water consumption. We also want to look at the Pearson R that shows the impacts and we also included some of these factors because they were significant in other studies, and we wanted to observe how those, right? So it seemed like, based on the MGWR, that the housing characteristics had the most significant impact in terms of impact on consumption, right? Specifically the habitable building area. Similarly, the same trends were found except for one, right? And the one that we found here with the MGWR that was different from the OLS is that population density actually led to a decrease. And this actually makes a little bit more sense than an increase because we have a lot more people compact into a lot more smaller spaces. So we're expecting water consumption to decrease, especially from the perspective of outdoor water use, right? We also did found, although it's not shown here, that increased population density did in terms of household individuals, like the numbers of individuals in a household, that did lead to an increase as well. Okay, so now why does all this matter, right? So we did all this analysis. How do we actually pair this to our high resolution data? Well, we were able to achieve a high resolution data set. It took a very long time and a lot of convincing and a lot of emails, but we were able to start to break down this high resolution data based on some of the factors that we found to be influential in the low resolution. Okay, so for example, and again, this is not complete, but I did want to share some of that with you. So we started to develop what we call empirical cumulative distribution functions, right? So essentially, it highlights the amount of data or the percentage of data that is less than a certain value, right? And we can plot that on a cumulative distribution function, and this will become very important later when we're talking about the simulation. Okay, so what we noticed was for some things, such as the number of toilet uses or the number of shower events in a day, number of individuals, which was one of the factors that we found to be influential, was very, very significant in the water consumption patterns, right? However, on the other side of things, some of the variables that we were looking at for the simulation, the start time, for example, did not seem to change significantly with the number of people that you had in the unit, right? So it was very interesting to see that how some factors changed and some didn't. So we're going to continue on with this exploration and starting to see how factors change. And then we can start to report on those results once that's finalized. Now, when it comes to actually linking the low resolution and high resolution data, we're going to continue, like I said, with validating those low resolution factors with the high resolution data analysis, but we also want to understand what is the actual use of these influential factors, right? So at the end of the day, we started to create a GUI, or a graphical user interface, using Python. And what we were able to do is we're able to input a location, and then based on the influential factors that are essentially defined by that area, we can then start to hopefully select those high resolution data sets that are representative of the water consumption, right? So you can see that down below where it says bidet frequency, clothes washer frequency. Those would be different based on different demographic and regional locations, right? Now, we don't want this to necessarily create a new set of variables for every location or every new project, because that would be impossible to enforce, as well as impossible to actually implement in the real world, right? So what we're going to do is we're going to use these variables, or our influential factors, to group or create groups of water consumption patterns that we would expect to be present in that area. Okay, so the location will reference to a series of consumption patterns grouped based on the similarities. Now, we also hope to link these a little bit further and hopefully use the low resolution data as an indicator, right? So our billing data as an indicator of what the high resolution data might be directly, instead of through these influential factors. And what we anticipate is, with the advance of what we call AMI, or advanced metering infrastructure, that's being installed a lot more frequently. And actually, a little tidbit is that they just recently sent out a contract to install all of the properties in Miami with these AMI infrastructure meters. So they're capable of a lot higher resolution. But we can essentially take that data, and then we can use our simulation method to justify whether, or validate whether, the consumption patterns that we have on record fit what we're seeing with that low resolution data. So that's kind of the link between the two. And that's what we anticipate to do in future research. Now, we've gotten to the point that we talked about influential factors and how they're going to change water consumption patterns. But we haven't talked about yet is the actual network-based demand estimation, right? how are these distributions actually used to predict water consumption in the built environment? So that's what we're going to start to talk about now. Now, when we look at the simulating water consumption, we have a few different factors that we want to consider. First of all, we need to understand how many events that are happening in a day, right? So if we go back to the beginning and we think about our demand simultaneous estimation, we need to figure out how many events for each fixture is happening in a day. So in order to find this, and again, the math here looks incredibly complex. It's really not. What we're doing is we're setting up an empirical cumulative distribution function, right? So this tells us what percentage of data is below a certain value. And then we're using random numbers. You can see that with the little computer from 0 to 1. And essentially, we're taking the inverse of the function, right? So we're taking that p as our y value, and then we're figuring out what x value corresponds, right? So for example, for a p of 0.67 or around there, we're going to have a corresponding event or number of events at 2, okay? So we can do this for each fixture, and we can figure out how many events are going to happen within a given simulation period. Now, each event can be represented by 4 characteristics. The first of these characteristics is the event duration, right? So if we go back to our thought that each water event can be represented by a pulse, this is changing how wide our duration or our event's going to be, right? So again, it's changing the width. The second factor that we have to consider is the start time. And this is essentially a translational shift, right? So if you look below, there's a little timeline that shows start time for a given event, right? So the start time, also calculated with an empirical cumulative distribution function that you saw earlier in the analysis tab, allows for this block to shift left or right, okay? And then the final aspect is going to be the hot and cold ratio. What portion of this water use event is hot water and what percent is cold water? Now, we've also discussed that flow rate is a significant factor, but in order to be a little bit more conservative in our calculation, we're going to be assuming that the maximum flow rate for a given fixture, which is actually dictated by standards and regulations, we're going to assume it to be the maximum, right? So we don't underrepresent what could happen, okay? So understanding all of this, we've generated now a series of events, right? You can see this on the left-hand side for each one of our fixtures that have their own start times, their own durations, their own flow rates, their own mix of hot and cold waters. Now, what do we do with all of these events? Well, we take the start time and then we rank them in order, right? So this creates what we call a discrete end use event simulation, right? So these discrete event simulations consist of a series of points in chronological order, or a series of events in chronological order that have an impact on the system. Now, when we go back, and again, this is a picture from earlier, what we can do is then we can start to stack them and determine what is the maximum flow rate going to be given these events. Now, this is all great, and this is something that has been done before in terms of stochastic methodologies. What hasn't been done is applying these events to a network, right? So this result will get you, for one pipe, the expected flow rate. And again, that's great, but that's inefficient. So what we started to do was applying the network events to a network, right? So what you're seeing here on the right is the actual process for a user to define the network. Again, this is something that we had in the graphical user interface that I've developed using Python, where we start to lay out all of the different fixtures that can be in a plumbing system, right? So you're seeing me enter a lavatory, a water closet, and then the shower coming up. And all of these are fixtures in the plumbing system. Once we get to a point that we're satisfied with our layout, we submit this, and then we have step 2, which is the auto allocation of fixtures to hot and cold networks, right? So it's very important to understand that not all fixtures are going to be in the hot and cold network. Some of them only have connections to cold water, right? So for example, water closets only can accept cold water. There is no hot water. Whereas on the other side of things, for in the United States, dishwashers only accept hot water, right? So these networks are going to be very different depending on your layout. So what I'm doing here is showing how a user could go through and essentially define these networks. So they lay out the joints, and then the arrows represent the flow rate and the pipes in the system, okay? So we end up laying all of these out, and then you create your individual networks, okay? Now what happens is we take our results from the simulation and then we can apply those to our schematic layout, right? The one that the user just defined. Now, how does this actually work, right? So right now, what I'm showing is the simulation trial results. On the left side, we have a black dotted line. It's vertical, right? So during that time frame, there are no fixtures that are active. So the simulation is going to show that nothing in the network is on. Now, as we switch and we get to a point where our fixtures are activated, this is going to update the network in terms of it's going to essentially turn fixtures on, right? Now, the characteristics of each of these events is going to impact all of the piping that leads up to it, right? So as you can see, let's give an example of the green dot that we have in the top left of our network, okay? So when that is updated or turned on, the characteristics of that are applied to all of the pipes that are leading up to it, right? So all of the pipes that are what we call upstream or opposite the direction of flow. Now, the summation of all of the active fixtures is going to be what we consider to be the current state of that pipe. Now, what happens is once we run through an entire simulation, we can then record all of these maximum flow rates that each pipe experiences. Now, it's important to notice that some of the maximums or most of the maximums do not occur given the same conditions, right? So we're only looking at that maximum flow rate for a given pipe, right? So we have this network where we have multiple trials, right? Because we do this multiple times in order to kind of come to a conversion on our data and our results. So we have multiple trials that lead to multiple flow rates. And then we can take these flow rates that we have and then start to apply them or create distributions, right? So over all of the trials, we create an expected outcome of maximum flow rates that this pipe may experience. Now, I'm going to just jump back 1 second and say that as we get further away from our end nodes, our terminal nodes, or we get more and more fixtures that are a part of a pipe, the probability that we have higher loading is going to decrease, right? Because we have a lower probability that we're going to have multiple AshCliff fixtures, right? So the pipes that are leading up to an individual fixture are most likely going to be very specifically related to that fixture, whereas upstream of these, where we have multiple fixtures, it's going to be a lot less than the total maximum capacity. Okay, so what we do is then we can take all of these simulations for the different trials and we can create distributions of expected flow rates. We can then size our pipes based on given parameters such as the percentage exceedance, right? So how reliable do we want the system to be? What are our maximum velocities? The residency times we want to expect. And based on this, we can then create accurately sized plumbing systems. Now, there's other factors or other information that we can pull from this simulation in terms of our design parameters and our data. We can also start to look at the actual sizing methodology of equipment, right? So in most cases, because of the way that pumps work, we don't need to size our pump systems to our 99th percentile, right? We want to design it to the average because again, we don't need to, pumps operate at various ranges. Now they're most efficient at their peaks, but we now design them at the maximum. So we can start to modify these design, and again, I'm not going to go too far into it, but we can start to modify how we design equipment based on averages rather than the 99th percentile. Okay, so that's how the sizing methodology works. Now, what does that actually look like in terms of results to the user? Now, again, we're going back to the GUI that we're developing. So as the system, and it appears we're missing the distributions, but regardless, as the system runs a simulation, we start to apply all these. What the user is going to see is this network right here. So we're going to see the hot and cold networks, okay? And then what the user is going to see is as they click on individual pipes, it'll pop up with a few different parameters and distributions. First of all, it's going to talk about one of the distributions that will be shown is the expected flow rates, right? And the actual design thresholds for a given pipe, right? So if you chose a 2.5-inch diameter versus a 3-inch diameter, where is the flow rate falling throughout that, okay? The second thing this is going to look at is the noise generated from turbulence, right? So that was one of the things that we considered a failure criteria. So we want to start to look at what is that noise generation? Because if it's too loud, maybe we have to bump that diameter up a little bit so that we don't have as much turbulence. We want to also, because we now have a two-dimensional representation, or in some cases three-dimensional, of our system, we can then also look at the pressure losses associated with with our current layout, right? So if we notice that there's a pressure drop that's too significant, we can start to work on improving the design in order for this to be a more feasible and user-friendly design, okay? And then we can start to also look at the expected velocity ranges to make sure those aren't exceeded to create those system conditions in which we start to see system failures, okay? And then once the design has been verified by the designer, the program will then auto-export the simulation summary as well as the design selection. So you'll have a nice, neat report that you can submit as you go to turn your design in to the building department, and it will be something that is easily on the other end of things. We can start to automate the actual verification from a building code perspective. So this kind of brings me to the final part of my presentation, which is the standardization of data collection. And we're going to talk briefly about why this is important on the next slide. Okay. So again, we talked about it a lot, but if we don't have enough data, then a system like this isn't going to be feasible, frankly, right? So we need to be able to standardize this system, collection system, the data collection methodology, so that we have a more standardized process and we have more standardized data that we can do analysis on. Okay? We don't have that as of right now. This is not something that exists. So in order to create something of that magnitude or of something similar, we have to identify what the failure points in a system are, right? So we can start to identify where we need to introduce this equipment, the frequency, and other parameters, right? So we started to look through all of the literature that we'd read, and we started to identify where are the failure points. First of all, we identified hydraulic events, incorrect temperature, and inaccurately predicted flow rate. We talked about inaccurately predicted flow rate, but incorrect temperature can lead to a lot of different unintended consequences, like the unmet thermal comfort and or efficiency, insufficient temp for sanitation, frozen pipes, leaks, burst, excessive water consumption, right? So on the other side of things, we have hydraulic pressure gradients, right? So water hammer events that can lead to equipment failure. So through identifying all of these failure criteria, we can then start to understand what we need to do or what we need to standardize in order to create data sets that are more available and more affordable. Okay. Now, again, we talked about this before, the lack of affordability of high resolution data sets, right? So we talked with, again, an industry partner, and again, it was on a scale of 100,000 to, even millions of dollars for this data. So what we decided was that we needed to first identify which parameters based on our failure criteria needed to be monitored, where the equipment needed to be installed in order to get the correct insights from this, how frequently we needed to collect data in terms of the actual data collection for individual equipment. And then we also needed to figure out the appropriate metadata, which is then drawn in from the influential factors, right? So once we understand those influential factors, how can we start to collect that data so that we can link those two and start to reach our ultimate goal, which was combining or finding a link between the high resolution and low resolution data. So what we decided was we wanted to create what was called SPADE, right? The System Performance and Data Extraction Guidelines. So what we wanted to do was identify which parameters to observe, and through literature review, we were able to do that. So we identified we needed flow sensors, which again was for distribution development, pressure sensors to observe theoretical versus actual pressure losses, and we also needed temperature sensors, right, to look at the thermodynamics of a system and start to look at what points are we going to have issues associated with incorrect temperature that could lead to the development of pathogens. Now, in terms of where and how much we need to monitor, specifically for high-rise buildings, we wanted to use the existing data set that we had, the high-resolution one that we're starting to break down, and use bootstrap sampling to determine the sensitivity of these water consumption events and their patterns. Once we understand the sensitivity, then we can start to create a generalized guideline for how many units inside of a high-rise residential building should be monitored, right? So to give an understanding of what's actually happening in that building, and if these user consumption patterns match up with what we're expecting them to. On top of that, we wanted to use influential factors. Based on the influential factors, we wanted to create surveys for the people that are in these units that we're monitoring to collect the metadata that then pairs with high resolution data to reaffirm that this is actually, these factors actually have an impact on these water consumption events. And finally, we wanted to determine the frequency. And again, for this is actually missing one point, but for flow sensors, it's going to be different than pressure sensors and temperature sensors because of the magnitude of how fast they change, right? So for an example, what you're seeing here is that the flow sensors can be collected at 1 to 5 second intervals. And that's enough to be able to disaggregate them and start to understand the actual distribution development. Whereas the pressure sensors now need to be collected at much higher resolutions or much faster frequencies because of the rapid changes that can occur within a system. And temperature systems can be opposite. They can be collected minutes to 10-minute intervals because, again, these don't change significantly fast, right? So moving on to that, we actually started to implement something like this. It didn't end up working out exactly how we wanted to. So in the old Stanford building, the high-rise residential buildings that we had on campus that housed students that were just torn down and replaced with a Centennial Village, we were able to install flow rate equipment and try to collect these data based on our SPADE guidelines. Unfortunately, the equipment that we got was malfunctioning. We tried to call in some experts to get these to work, and it still didn't work. So we actually were not able to obtain the results that we had hoped for. But still, this is the process that needs to be followed in order to validate the concept that were developed through SPADE. Okay. The other aspect of this, and something that we want to do moving forward, is expansion of this monitoring to sanitary. And this gives us insights into a whole different aspect, which has a lot of different problems. Okay, so first thing, again, we have to identify the failure criteria, which we've already started to do. We need to establish the appropriate parameters, which again are very similar to what we have. But we have to then establish locations and frequencies, and this is where it changes quite significantly from the supply side. So that's future work that we're actually working on ongoing. And then we also want to expand these data collection guidelines to other occupancies, right? So we talked about hospitals, commercial buildings, arenas, assisted living. We want to expand these methodologies to be modified and give us insights on those occupancies so that once we get those patterns, we can then create the exact same concept that we're doing with the residential and expand to those other occupancies. Okay. All right, finally, and this is the last slide, we're going to talk about the research implications. So as we talked about before, this methodology can develop a new and modular framework that designers can use to optimize and rapidly design plumbing networks, right? So this increases productivity from the perspective of the designer, but it also creates a correctly sized piping system, which again minimizes the negative impacts associated with these incorrectly sized systems. On top of this, this has implications for water reuse systems. We start to look at the sizing of day tanks and water reuse equipment, as well as other equipment such as pressure reduction valves, pumps, and a few other pieces of equipment that are necessary for plumbing systems. In addition, these results, the outcome of these results, especially from the simulation, can be used by utilities to determine the impact of developments on municipal water supply. These results, especially, again, the simulation results, in terms of flow rate, my apologies, in terms of the end use simulation, the discrete event simulation, those can be plugged into softwares like the EPA Net to validate the system performance, as well as the water quality. And then we can also use this as a checking mechanism to validate retrofitted systems within certain operational conditions to make sure that they're operating as expected. Okay? And with that, I'd like to thank you everybody for attending, especially, you know, I've had a great experience here so far, and I know most of you, and you've all contributed a lot to this project, either through talking to me. So thank you very much. And if you have any questions, please feel free to let me know.